Okay, this is a lesson on student learning task 5. And by the end of this lesson, you will be able to write the equation for the length of a shadow produced by a Ferris wheel. And we are also going to solve problems involving an angle of elevation or an angle of depression. So let's turn, if you're in my class, to page 40 in our packet and read the scenario. Again, we are dealing with Carlos and his Ferris wheel. In spite of his nervousness, Carlos enjoys his first ride on the amusement park Ferris wheel. He does, however, spend a lot of his time with his eyes fixed on the ground below him. After a while, he becomes fascinated with the fact that since the sun is directly overhead, his shadow moves back and forth across the ground beneath him as he rides around on the Ferris wheel. Recall the following facts for the Ferris wheel Carlos is riding. The Ferris wheel has a radius of 25 feet. The Ferris wheel is 30 feet above the ground, and it completes one rotation counterclockwise every 20 seconds. To describe the location of Carlos's shadow as it moves back and forth on the ground beneath him, we could measure the shadow's horizontal distance in feet to the right or left of the point directly beneath the center of the Ferris wheel, with locations to the right of the center having positive values, and locations to the left of the center having negative values. For instance, in this system, Carlos's shadow would have a value of 25 when he's at the position to the farthest right. So as a reminder, ooh, that's a bad circle. So like if this was, we call this chair A is furthest to the right and the radius is 25. So at chair A, we would say the shadow is positive 25. And then if we were on the far left here, it would be negative 25. Number 1 says, what would Carlos's position be on the Ferris wheel when his shadow is located at 0 in this new measurement system? So if this new measurement system, for him to have a shadow of 0, he would have to be at the very top or the very bottom. Okay. Number 2 says, sketch a graph of the horizontal location of Carlos's shadow as a function of time t, where t represents the time after Carlos passes position A. So before we do that, let's again just draw the little Ferris wheel here. Here's our little, we're gonna do what I like to call the lollipop Ferris wheel. So we really don't need the height of 30, but we'll just put it there. So we start here at 0. So when time is 0, the shadow is 25. Okay, so at the very top, remember it's 30 seconds to go around. So up here, this is going to be 5 seconds. And at 5 seconds, the shadow is going to be 0. Over here will be 10 seconds. And because that's the far left, 10 seconds will be negative 25. 15 seconds will be at the bottom. That will be 0. And then 20 seconds will be back at chair A, 25. So we're going to label this just as a reminder, or not really a reminder, FYI, this graph messes people up. This is not -5, -10. It's just the way the scale overlays the grid. Those are just the grid lines. So those are not negative numbers. These are negatives down here, though, of course. So go ahead, take a minute and graph. And I'm going to assume that this pattern continues. So 25 at the top, 30 the far left, 35 the bottom, and 40 the top again on its way back down, because this will be here. So I'm just going to go ahead, sketch this graph to the best. Oh, that's a little off. That's okay. That's actually really bad. Let's add that better. All right, here we go. Oops. Oh, well. I'm just going to go with it. There we go. Okay. So be sure to label our graph. This is the shadow length. And this is time in seconds. All right, so on page 41, it says calculate the location of Carlos's shadow at times t using the following table, where t represents the number of seconds since Carlos has passed the furthest position. Now you'll notice that when I made my graph, I counted by fives because I knew that this was 0 seconds, this was 10 seconds. So I know 10 seconds is going to be negative 25. I know that 0 seconds would be 25, but I don't have a 5 here. So I need another way to do this. So what I'm going to do is I'm going to go ahead and I'm going to drop a perpendicular from chair B to spoke A. This should feel familiar. I know from previous problems, I know that this is 36 degrees, and I know the radius is 25. The difference is now I'm looking for this shadow length. So let me grab my highlighter. So what I'm really looking for is I'm looking for this shadow length that the Ferris wheel is going to make. So if I'm looking for this, that's going to be from 36 adjacent and hypotenuse. So this is going to be the cosine of 36 equals x over 25. So my calculation for 2 seconds will be 25 cosine 36. Let's put it in 25 cosine 36. And I get 20.2. Ooh. Feet. So now if I go to do chair C, again, this is going to be just like before. I now have an angle of 72. So my calculation is going to be the cosine of 72 equals x over 25. So at 4 seconds, 25 cos 72. I'm just going to change that angle. And I get 7.7. Okay. Okay. And I can go ahead and do now again, just like we did before, I'm going to now use symmetry. So here, once I pass the height, remember everything that's over here, this is a positive, and everything that happens to the left is a negative shadow. So when I go to chair D, it's the same absolute value length, but now this is going to be negative 7.7 feet. And chair E at 8 seconds will be negative 20.2 feet. 10 seconds is negative 25. Now the difference from before is that chair E and chair G, they actually produce the exact same shadow. Okay, it's not a height, it's the shadow length we're looking at. And then negative 7.7, keep forgetting the feet. Then when I'm down at the bottom, that would be 0. And then when I get to chair I, that's still going to be negative 7.7. And then negative, oh, whoops, positive, we passed. And then positive 20.2. And then at 20 seconds, we're back at chair A with a shadow of 25 feet. So now the question is, can I write a general equation that can give us the calculation of the shadow? So I'm noticing they all start 25 cosine. So I'm going to say the shadow S at T is 25 cosine. Now, just like before, I'm going to look at this, and this is for 2 seconds. So if 36 is for 2 seconds, that means 1 second will be 18. So in the parentheses here, I'm going to put 18t because it's 18 degrees per second. All right, so we did that letter. We did number 4. We just kind of did it up here. There's our general formula. Let's take a look at angles of elevation and angles of depression. Oh, wait, no, I'm a big liar. First, we got to look at page 42. So we actually did all of these problems prior You can pause the video and look back at 26 to get the lengths of the radius. Remember, this is 4, this is 3, this was 5, this is -4, this is 4√3, this is 8, and then this was 1, this one was 12. So now we're being asked to, given the point on the circle, find the value of cosine. And to recall that cosine is x over r. So for number 1, when I do the cosine of theta, I need x over r, x is 4, and r is 5. Number 2, x is -4, r is 8. Number 3, x is -√2/2, and r is 1. Well, anything divided by 1 is itself. Number 4, x is 6√3, r is 12, and I can reduce these. So I get √3/2. Before we take a look at angles of elevation and angles of depression, we're going to just look at cosine of our quadrantal angles. So here we've got a beautiful circle, a unit circle, and all the quadrantal angles are labeled. I'm going to put the degree measurements on them. So this is 0, 90, this is 180, this is 270, and 0 is also 360. So I have my x and y values labeled, and I can see that the radius of this circle is 1. So because cosine of theta is equal to x over r, for 0 degrees, oh, 0 is not here. That's okay. I could skip that guy. 90, x is 0, r is 1. 0 divided by 1 is 0. For 180, x is -1 divided by 1. -1 divided by 1 is -1. 270, x is 0, r is 1. For 360, there's the 0. They're the same. They are coterminal angles. X is 1, r is 1. So we get 1. Again, I'm just going back to this cosine of theta equals x over r, grabbing the x coordinate and dividing it by the radius. Okay, now let's talk about angles of elevation and angles of depression. You might want to pause the video in a minute and jot this down, but I'll show you exactly what you need to jot down. So both an angle of elevation and an angle of depression are in relation to this horizontal. You'll notice that you have this scary little man up here, and he's got this sight line that goes across. His sight line is a horizontal sight line, and the angle of depression comes down from that sight line. Then you have this little person on the cute boat, and she's looking straight out on her sight line, and the angle of elevation comes up from the sight line. Now, they are both horizontal lines. They are parallel. From geometry, we know that if we have two parallel lines cut by a transversal, in other words, this transversal that is the connection of their sight lines, alternate interior angles are congruent. In other words, this alternate interior angle and this are congruent. Does that mean the angle of elevation and the angle of depression are the same? No, it does not. It just so happens that these two little people, their sight line is the same. They are looking at the same, they're looking at each other. So let's take a look at some situations. This is your homework. I'm just going to help you draw a few of them. It says a kite is aloft at the end of the string, and the string is 1,500 feet long, and the string makes an angle of 43 degrees with the ground. So that is an angle of elevation. So I'm going to draw, here's like yellow person here. Here's the kite. If I were to draw the kite, I would have like, I don't know, I can't draw a kite. Here's the ground. Here's the string. Kites are normally like a triangle or a diamond. So then it's like, you know, there goes to the end of the string. And I know the string is 1,500 feet long. And I know the string makes an angle of elevation up from the horizontal of 43 degrees. I'm looking for how far above the ground. I'm looking for X. A ladder leans against a building. And then you actually have to solve these. I'm not solving them for you. So a ladder leans against the building. The top of the ladder reaches a point on the building that is 12 feet above the ground. The foot of the ladder is 4 feet from the building. That is so not to scale. Find I need the measure of the angle. So I'm looking for that angle here. I'm going to draw a few more of these and then you are on your own to solve them. The shadow of a flagpole. So I know the flagpole is 40.6 meters. Oh, the shadow is be a good reader, Strauss. Shadow. 0.6. This is the flagpole. Flagpole. So I'm looking for the height of the flagpole. And I know that the angle of elevation of the sun, but it's an angle of elevation. So there we go. I should probably bring to the sun, but that's okay. Is 34.6, and you are able to solve that. The angle, this is the best one. The angle of the depression from the top of a building. Here's my building. Here's the horizontal. Here's the car. I'm not drawing you a car. Is how far from the top of the building is the car on the ground? If the building is 252 meters high. So here's the thing, you can turn this picture into a rectangle, or you can know that alternate interior angles are congruent, and you can mark this as 0.5, and we are looking for how far the car is from the top of the building. So we are looking for the hypotenuse. Okay, at this point, you should be able to solve these 4 problems. The answers will be in the class notes file.